Hi, welcome back for section 7.2. In section 7.2, we're going to take what we did in section 7.1, that is the idea of estimating a population parameter, and extend it from just doing the population proportion to doing a population mean. So what if I wanted to find the estimator for a population mean, right? So we're basically going to redo what we did in 7.1, except for instead of using p-hats to estimate p's, we're going to use sample means, x bars, to make a estimation for a mu, a population mean. We're going to build confidence intervals again. It's just instead of the confidence interval being an interval around a p-hat, it's going to be an interval around an x bar. So our point estimate will just be a sample mean, and our confidence interval will then estimate a population mean, right? And then we're going to talk about sample sizes and how to find the right sample size to do the thing you want to do. Okay? Now, there are two scenarios here. We'll start by taking a look at the more realistic scenario, and then we'll also talk about the less realistic scenario. The realistic scenario is we're going to build a confidence interval for a population mean with a population standard deviation that is unknown, which is exactly what you'd walk into it. You'd walk into it going, I don't know. So I want to estimate how much soda is in my 12-ounce cans of soda that I'm making down at the Coke factory or the Pepsi factory or whatever, right? I want to estimate that population mean, but I don't know it. I can't know it. And I definitely, if I don't know the mean, I definitely don't know the standard deviation. So the first thing I'm going to do is I'm going to go out and gather some data to do this. All right. So we're going to take a look at the realistic scenario where we don't know. So this is what we want to estimate. Okay. How do we do it? We get a sample of size n. From that sample, we develop a sample mean as well as a sample standard deviation. There's a formula that allows us to turn those into a margin of error. And then once we've got our margin of error, we say that it's going to be x bar plus or minus whatever that margin of error is, and then that becomes our confidence interval. Those ideas of the level of confidence, or the confidence level, those 99s, 95s, 90s from last section, same thing here. We're just doing it for means instead of proportions. Right? The requirements necessary for the math to work are that, of course, it's a simple random sample, and one of these at least needs to be true. Either the population from which we're sampling is a normal population, or our sample size is sufficiently large, usually bigger than 30. 30 is not a hard fixed number across statistics, but it's going to be a fixed number for us in this course. We're going to argue 30 every single time. Okay? And then once we have established that the requirements have been met, and we gather our data, we'll use that to create a margin of error. Okay, so the exact same concept for this that we used in section 7.1. And then we develop an interval around it. Now, there's one thing that is different from section 7.1. In section 7.1, when we did those population proportions, because the underlying mathematics was binomial, when we calculated things, we used that normal distribution as the math behind the scenes. Okay? The normal distribution is what gave us our z sub alpha divided by 2 values, the 1.645, the 1.96, and the 2.54 for the 90, 95, and 99% confidence intervals. Because we're now working with sample means, our sampling distribution will not be worked off of the normal distribution that we did before. We're going to be using something called the t-distribution or the student distribution. The reason it's got the weird name student distribution is because um, when the original individual was working on the math behind this, he published his information using the pseudonym Student as his last name. I'm not sure why or how that came about, but because it was published under the name Student, it is now called the student distribution. That's kind of an older name. Most people refer to it as the T distribution. And basically what it is it's this kind of thing. Right? The T distribution looks a lot like a normal distribution. And on this graph, the green one is your plain old normal distribution. That's the one we did with the norm CDF and all that stuff in the earlier chapters. The student distribution is the red one and the blue one. Now, here's where student distributions are definitely different. Student distributions care about sample size. Normal distributions did not care. The student distribution with a smaller sample, like 3 versus 12, you'll notice that a smaller sample, it's a little bit lower in the middle, and its tails are higher, which kind of pushes some of the probability away from the middle and out to those tails. When the sample size gets larger, like it is here with the 12, you notice that middle goes up a little bit and those tails come down a little bit. So when it's 12, the middle came up and the tails came down. And so what happens is, as the sample size gets larger in that distribution, the T-graph gets closer and closer and closer to that standard normal distribution graph. In fact, as soon as n hits about 30, if you graph the T distribution and the standard normal on the same set of axes, you wouldn't be able to tell the difference, which is where this requirement comes from. That's why that 30 is there. So it has all the same properties as a normal distribution. That is, it is symmetric about the mean. The area under the curve adds up to 1. It's increasing, and then it's peaking in the middle, then it's decreasing, and all of that stuff. It has all those same properties as a normal distribution. It just distributes the probability a little differently. It moves some of the probability from the middle out to the tails, which then, unfortunately, for small sample sizes, is going to increase the width of our confidence interval. But as long as the sample size is reasonably large, it gets this very close to a normal distribution look, which gives us intervals very close to what you would get from a normal distribution. All right? Along with this, though, you're going to run into this phrase that's going to show up whenever we talk about T distributions, about the degree of freedom. Since the T distribution depends upon the sample size, one of the things that they represent when they talk about T distributions, that they talk about the degrees of freedom of the distribution. The degrees of freedom is just a fancy way of saying n minus 1, sample size minus 1. So if I was looking at this graph right here, this distribution has a DF, or a degrees of freedom, of 2. This would have a degrees of freedom of 11, because the degrees of freedom is always the sample size minus 1. It is just a number that I need to do the calculations to make sure I'm using the right graph. So that's what that's talking about. If you're interested in looking at the math behind the scenes, the margin of error formula is this guy. The margin of error can be found by taking the critical value for the T, the appropriate T distribution, and multiplying it by the standard error on the mean. You remember that, where we took the standard deviation, divided it by the square root of the sample size? And then that's going to give us our margin of error. Okay? Now, how do you find numbers for this? Because for the last section, when we had z sub alpha divided by 2, I used that inverse normal command to get those. Right? And you can basically do the same thing with these guys. You're just going to use an inverse t command. So if you remember, under our distribution menu, that's where the inverse normal was, and right below it, see there, our inverse t. And so you would go there, you'd say what was the area need to be. So if I needed to make a 95% confidence interval, that means I'm looking at a t distribution where the middle is 95. This is 2.5. This is 2.5%. And to find this value, which is our t sub, what is that going to be? 5 divided by, so it's t sub 2.5, our critical value there at t sub 2.5. That left area is 97.5, so I will put in my 0.975, and then here it's asking me for the degrees of freedom. So okay, well, whatever n is, I would do it for 1 less. So if n was, I don't know what it is, 20, I would put a 19 in there, and it would tell me that it's 2.09. If I run that command again, and let's say instead of 20, we only had 15, well, then that would be 14. And you see how I get a different t value every single time? With the critical values for z's, 95% gave us 1.96 no matter how big or how small the sample size was. With t's, 95 gives me a different number every single time for every different sample size. But once my sample gets pretty big, like 30 or more, so if I get out there at about 29, which would be a sample size of 30, 2.04. And if I change that and make that be, I don't know, let's say a sample size of 40, which would be a degrees of freedom of 39, it doesn't really change much. We're looking at a change of 3 in the hundredths place, so 3/100ths difference. And if I went to a crazy big sample size of, say we went up to about a 200, which would give us a 199. Right, now I'm starting to see some change, but I had to make a pretty good sized leap in my sample size to get some good change to occur. So it doesn't affect it much once your sample gets big. All right, so let's take a look at what we're going to do. Our job is to construct confidence intervals for estimating population means. Someone's going to hand us data, right? And they're either going to be kind to us or not kind to us. And sometimes they'll take that data and perform those summary statistics. That is, they'll find the values for n and x bar and s, and we'll just use those directly in. Sometimes they'll just give us the set of data and we'll have to do the work ourselves. Right? Then we're going to take all that, we're going to run it through the formula, we're going to chuck it in the calculator, right? And we're going to find our intervals. Make sure we check and verify that our requirements are met. Simple random samples and normal distribution or a big enough sample size. Okay, so let's take a look at one and see if we can just walk it through. You randomly select 45 coffee shops and measure the temperature of their coffee sold. Okay. So I've got an N of 45. Right there, that tells me that my sampling is big enough. I needed more than 30. I got 45. I'm good. Okay. The sample mean temperature. Okay. So the sample mean temperature, the summary statistics, are 162.0 degrees Fahrenheit for the mean and a sample standard deviation of 10.0 degrees Fahrenheit for the standard deviation. My job then is to construct a 95% confidence interval for the population mean. So here's my sample data information. Can I turn that into a confidence interval? Well, can I? Well, I don't know the standard deviation of the population, so that's okay. My sample is random because I randomly selected. Good there. My sample is big enough. I'm good. I've got my sample statistics. I can make this into a margin of error. Right? So the first thing I'm going to do is I'm going to show you how one could do this by hand should they want to. Right? My margin of error will be my critical value for the t-distribution at 2.5% because I'm doing a 95% confidence interval, multiplied by, and there's the formula right up here in case you're wondering where this is coming from. Where's that formula? Sorry. Right there it is. So I had to do times the sample standard deviation divided by the square root of n. Right? So I know that the numerator is going to be 10. I know my denominator is going to be 45 under the root. Now I just need to figure out what this thing is. So I need to find a critical value for a 2.5t at a sample size of 45, which means degrees of freedom 44. So I'm going to go to my distributions. I'm going to do that inverse t, 95% confidence interval, so the left side is 975. My degrees of freedom would be 44. Paste that back in, and I get that a t, my critical value, t sub c, is 2.02. So I'm going to take that 2.02, I'm going to multiply it by 10, and then divide that by the square root of 45. And I get a margin of error of 3.01. So it looks like my confidence interval would be 162.0 plus or minus 3. I'm just going to take it to one decimal place. Right? And these are, of course, degrees Fahrenheit. If I wanted to write it as a true interval, I'd be looking at 159.0 degrees to 165.0 degrees Fahrenheit. Now, if I wanted to do the same calculation just using my calculator, I can do that too. Right? So I'm clear that out. I'm going to go back to stats, over to tests, and now I'm looking for not a confidence interval based on t values. So let's see, t interval, option number 8 on the TI. I'm looking for the confidence interval based on t's. T's because I have an unknown population standard deviation. Now here's where things get a little tricky. The first thing the calculator is going to ask me for is, where's the data? Are you just going to give me a list of values and I'll do all the work for you? Or are you going to type in the summary statistics? And since we have those, I'm going to just type them in so I make sure stats is highlighted. My X bar, my sample mean was 162. My sample standard deviation was 10. My sample size was 45. And I want a 95% confidence interval. Bada bing, bada boom, it spits it out. And it tells me it's 159 to 165, which is exactly what I got down there. So my calculator would just tell me 159 to 165. If I needed the margin of error, and I just had this, again, I can still figure it out. I know my point estimate is 162, and if I know that my point estimate is 162, and that this lower limit is always the point estimate minus the margin of error, and the upper is the point estimate plus the margin of error, I could always just take the upper minus the mean, so 165 minus 162, and get my 3. So my margin of error would be 3. Or I could do the same thing I did last section. I could take the upper, 165, subtract off the lower, 159, divide that answer by 2, and get that my margin of error is 3. So the same techniques we did before still work here for turning the calculator output into those individual values should you need them. Right? Remember, these are degrees and this is all Fahrenheit, right? Okay. All right, let's try another one to make sure. You randomly select 36 cars of the same model that were sold at a car dealership and determine the number of days that each car sat on a dealership's lot before it was sold. The sample mean is 9.75 days with a sample standard deviation of 2.39 days. Construct a 99% confidence interval for the population mean number of days that the car model sits on the dealer's lot. Okay, so I want to estimate how long this model car will sit on a dealer's lot. So I gather some data. Let's draw out some of the information. 36 cars. Our sample size is 36. All right. I ran the numbers and I found that I have a sample mean of 9.75, in this case, days, and a sample standard deviation of 2.39 days. I'm supposed to construct a 99% confidence interval. That is, it's going to have a confidence level of 99%, which means that it has an alpha level of 0.01 for this population parameter with this data. You could say it either way. Okay. Now I could do this by hand, but I'm lazy, so I'm not. I'm going to use my technology. Okay. So I'm going to grab my data and I'm going to put it into the calculator. I'm going to go to Stat, over to Tests, and I'm looking for that T-interval command again. Right? And I'm going to make a little note to myself over here. It's the T-interval command. Right? Punch it up. Right? I have the summary statistics, so I'll make sure that's selected over there. I'll put in the correct values. My sample mean is 9.75. My sample standard deviation is 2.39. My sample size is 36. They want a 99 one here. Okay, 99% confidence level. And I press enter and I get this. I'm just going to copy it down over here. 8.665 to 10.835. So that means it's rounded correctly. Since everything else is 2 decimal places, I'll go 2. 8.67 days to 10.84 days. And if they wanted the margin of error, I can find that. I'll take the upper of 10.835, subtract off the lower of 8.665, and divide that by 2. And I get a margin of error of 1.09 days. So putting it all together, what can I say about this car model on these lots? Well, I can say that with a 99% confidence that the population mean time that these cars will spend on the lot is between 8.67 days and 10.84 days. Or if you prefer, 9.75 days plus or minus 1.09 days. Okay? Because we could say it that way as well. We could say 9.75 days plus or minus that 1.09 days. Okay. We can express it as an interval, or we can express it as a point estimate plus or minus a margin of error. Right? Which way is the right way? There is no right way. It's just how you choose to do it. Okay. All right, we're looking at about 24 minutes right here for this video, so I'm going to stop this one. We'll come back and we'll take a look at the rest of the section in the next video. See you back here for part 2.